Can everyone hear me? Great. I can hear me. These mics are so loud. I love it. All right. This is the second Kafka session of the day. I'm back again. I brought a plant with me for those of you who weren't at the one this morning. I like plants. But this is a different topic, still on Kafka. My name is Danica. I'm a developer advocate at Confluent, and that naturally means that I am a Apache Kafka person. I kind of like Kafka a lot. But today, we're not just talking about Kafka, we're going to talk about as well. I don't know if anybody got the references in this. Oh, you will. It'll hit you in the face. Okay. Anyway, so let's talk about Kafka. Specifically, you're all here because you don't know how to get data into Kafka, right? Or at the very least, you probably take it for granted. How many of you are working with Kafka on a regular basis? Cool. And I guarantee most, if not all of you, are just building clients on top of Kafka, right, to interact, send data to, and consume data from Kafka. So we're going to see a little more into the inner workings of getting data into Kafka and the whole process, right, because it's a beautiful black box that you thankfully don't need to think about 99% of the time, except for that one time when it doesn't work and you're really frustrated. So let's try to alleviate those frustrations, make this a little bit easier for us. So let's get data into Kafka. What are we going to do first? Well, we're going to start with a schema because we are reasonable humans. We're not just going to go rogue and throw some random data into Kafka. So here is a simple schema that I defined. So we are going to deal with the whereabouts of hobbits, naturally. That seems like a data worth keeping track of. So what do we need? We need the name of the hobbit, who we're dealing with, where they currently are. And, hobbits don't do too much, so we have a limited subset of things that they could currently be doing. Great. This is going to be our Hobbit update schema, and we're going to create a corresponding topic to store this data in. Hobbit updates, that makes sense. And we'll get into these configurations a little bit more, but I wanted to show which configs I actually used to create this topic. So the number of partitions, that's important in Kafka. The replication factor, how many copies of this data we should have across the cluster. Min in-sync replicas, how many copies we should have in sync to consider it healthy. And how we would clean up this data later on when it gets old or stale. So pretty simple. This is how many of you start when you're dealing with your data, right? You have a schema, you want to write some data, and you have a topic that you want to put it in. Cool. So let's write some data. Okay, we're going to build up an object. This is going to depend on what language. I'm trying to keep this client agnostic, so whatever language you want, you're going to have to look into the specifics of that sort of client, but keeping it generic. So we're going to build up this event. We need a key because, again, we're reasonable humans, so we're going to have a string, Bilbo Baggins. That's a reasonable hobbit for us to want to write data on. Keep track of his name, his location. He's where he should be at Bag End in Hobbiton. And he is eating, as hobbits do. I mean, it's 11 right now, so that's what he's doing. And we're going to build up this object, and we're going to call producer.send and ship it off to Kafka. We're done. It's over. You can all leave. That's simple. Or that's probably what many of us do, right? When we're working with Kafka, okay, you get your data, you ship it off, we're done, okay? Because the data's in Kafka, right? Yeah, kind of. Sure. I'm not saying this to make you worried that your data is not in Kafka, okay? You shouldn't be worried. But, for all intents and purposes, as soon as you call producer.send, yeah, your data is on its way. It's making progress, okay? Is it necessarily in Kafka at that moment? Probably not, okay? How long it takes for the data actually be written to the broker and actually get to where it needs to be, that could vary. The steps that it goes through, they're generally going to go through all the same stages. But how long the time period that this takes is going to vary, right? It's not just going to instantaneously be on your Kafka cluster, okay? And it's more of a journey. It is. It really is. Again, it's abstracted away from you, but there's actually a lot of stages that we're going through before that data makes it onto the broker. And here they are. Bask in the glory of this beautiful, beautiful diagram that I did not make that shows all of the stages from a producer client all the way over to disk and coming back to the producer again. There's a ton in here, and we're going to break all of these down. You don't need to think about all of these right now, but these are all the stages we need to go through before our data is durably stored, before we know that it is on the cluster. But before we actually get into all these stages, right, there's two sections here. There is the client outside of the broker, obviously. that you are mostly interacting with. And then we have the stages inside the broker where there's a lot going on in there, right? But it shouldn't surprise you that actually half of this journey happens on the producer side, on the client side. Because like hobbits, we are stubborn creatures. And if we want to go somewhere, if our data wants to go somewhere, well, we need to prepare. We need to pack our bags, and it's going to take a little bit of time for us to actually get going on this journey. All of this starts at home, in Bag End, in Hobbiton, on the client side with our producer. Okay, so let's dive into this now. We started with an event, right? We've got Bilbo in Bag End eating. And we've called producer.send, we want to move this data into Kafka. Well, first step is that, am I going in and out? I'm going in and out. Hopefully, okay. We'll make do. I'm loud enough, so hopefully in the back you can hear me. All right, the first thing we need to do is take the object that we've built up, that Hobbit update, and serialize it according to that schema that we have defined, right? Because the brokers don't care about objects or strings, they care about bytes, all right? So these messages can be anything. They can be objects, they can be a string, whatever you want to actually build it up. But the fact of the matter is it needs to be bytes in order to actually be stored on the broker. So the first thing we need to do is serialize that data. And the important part of this talk is that I want to give you the tools, give you the configs, give you the metrics that you're going to be using at each one of these stages so that in the event that this doesn't quite work out like it does 99% of the time, that you know where to look, okay? So at this stage, there are two configs you can use. There's the key serializer, there's the value serializer. So you can control these serial. I get the fun mic now. No? Leave it? What are we doing? What are we doing? Okay. Do we get, when we do the edit of this, I want like the rainbow screen that comes up that's like, yeah, good? All right, cool. Let's get back into it. So two configs that you can use here. You can serialize the key independently and the value independently. Great. So we serialize that data according to that schema. And next is we need to figure out where that data actually goes, which partition it should live on. Because remember, we have 4 partitions for this topic that data is destined for. So there's a few main configurations that impact where this data actually goes. The first and the biggest one is partitioner class. This defines at a high level how your data is going to be partitioned, and you have a few options. So there's the default, thankfully. The default partitioning logic says, if there's no partition specified as part of the message, which is completely reasonable, you don't have to define that outright, but there is a key, and remember there is a key that we defined for our message, then we're going to choose a partition based off the hash of that key. And that makes sense, right? So that every event that has the same key, we're going to hash it to the same partition, and we ensure that that data is where it should be. If no partition is present, and there is no key, which again, you're free to do, then we're going to use a sticky partitioner. It's just a little bit more efficient, and it's going to uniformly distribute our data. So we're going to group a bunch of data together and ship it off to partition 0. And then we're going to do the same thing and ship it off to partition 1, 2, 3, and keep going. So again, we're uniformly distributing that data to the best of our ability. If you don't want to use the default functionality, you can use the round-robin partitioner. That is exactly what it sounds like. And I'm going to say that a lot during this. I feel like there are a lot of configurations and metrics in Kafka that maybe are just poorly named. And so I really want to call out the ones that do it well. So round-robin partitioner, each record in a series of consecutive records, we're going to ship it off to a different partition. So partition 0, then 1, then 2 and 3, and so on and so forth. We're going to keep going around. And it would seem like that data would be uniformly distributed, but you'd be surprised. It isn't always. So if you want that uniform distribution, it's better to use the default partitioner. And finally, if none of those work for you, if you know what your data looks like, if you know how it should be distributed according to partitions, and you want to avoid hot partitioning, then a custom partitioner might be better for you. I see this come up a lot in like financial services use cases to avoid market data. Particular securities are more frequently traded than others. So that's an option for you as well. And there's a couple other lesser known configurations that impact partitioning. So the first is partitioner ignore keys. So if you want to, again, exactly what it sounds like. If true, we're going to ignore all the keys, even if they're set. for partitioning. So if you really, really want your data to be uniformly distributed, but you still want to use keys, so you're going to use the default partitioning, and then you're going to set this to true. Okay. Other lesser known partitions configurations, we have partitioner adaptive partitioning enable, which it's pretty cool. It looks at how quickly the brokers are processing the incoming messages and for that topic, and then adapts it to send more data to the faster brokers and less data to the slower ones. In conjunction with that, we have the partitioner availability timeout MS, which only works in conjunction with the previous one. If a request to a given partition takes longer than this timeout, then we're going to ignore that partition for a little bit, give it some time to catch up. Okay? So partitioning, cool. We've defined a partition based, in this case, on the hash of that key for that message. And we've serialized the data, we know the partition, cool, we can ship it off to the broker, right? Well, not really, because it might be more efficient for us to group a bunch of data together and then ship it off to the broker, right? It's better for throughput, most of the time better for latency. If the messages are batched together by their destination brokers, then we can be a little more efficient in how we're sending this data, okay? And there's a number of really important configurations. So how many of you batch when you deal with producers? Okay, only a couple of you are aware. Look into the code. Batching is a huge part of Kafka producer clients, okay? And as soon as you start pulling one of these levers, other ones are affected. So this is, I feel like, the biggest configuration issues that I see with producer clients have to do with batching. Okay, so pay attention. So the most obvious thing that you would want to control for your batches is how large the batches are, right? So keep in mind that a single batch will only contain records destined for the same partition, okay? So keep that in mind when you're defining this size. The default is 16 kilobytes. A few more things to note here. If your records are larger than batch size, you're not batching, okay? They're obviously not going to be batched. So understand what your data looks like, okay? If this value is set to 0, batching is disabled, and you're not batching. If you set this to be small, right, some small value, then you're going to have more frequent sets of smaller batches sent to the broker. This means that overall throughput might go down, okay? And we're adding round-trip time to make requests with fewer events, right? On the other hand, if batch size is larger, then you could potentially increase throughput, but you might be running the risk of running out of memory on the producer side of things, and you might be hanging around waiting to fill that batch too long. So you might actually add additional latency too. And keep in mind that batch size is just an upper bound for the size of this batch. You're not always going to hit that value. There's also a time-based threshold, which is linger MS, okay? So this is how long we're going to wait, the upper limit that we're going to wait for, to try to fill that batch up until batch size, okay? Linger MS is set to 0 by default, meaning that we're not going to wait at all to accumulate records. We're not batching. As soon as we get an event, we call producer.send, ship it off, right? If you want to batch your data for better throughput, know that you are doing this at the expense of potentially adding latency, right? So whatever you choose for linger MS, you're potentially adding that much latency to every request, okay? That said, we can also actually improve latency by reducing pressure on the brokers. So it's this dance whenever you decide to batch. Batch size and linger MS, they go hand in hand, right? They're both upper thresholds controlling batches. So once one of them is hit, then we're going to ship off the batch, okay? Another final overlooked configuration is buffer memory. As we're sitting around trying to fill these batches, we have to store the data somewhere, and it's going to be local on that client, okay? By default, this is about 32 megabytes, but the producer also uses some additional memory on top of that, so keep that in mind if you're containerizing maybe. Obviously, buffer memory should be larger than the batch size, or you're going to run issues, okay? Another thing to note is that the producer is going to break, once you allocate this memory, it's going to take that chunk of data, and it's going to break it into batch.size-sized chunks. Okay, so it's going to pre-allocate where we're going to put these batches in memory to store them until we ship them off. Okay, so this value is directly going to affect how many batches you can ship off at once or work with in conjunction. Like I said, changing these configurations for batching, it is a dance. It is a difficult dance, so you should know what you're doing. And you should also monitor, right, and understand how well you're doing if you want to be optimal in your batching. So we got to use some metrics, okay? So striking this balance, how do we do this? The first thing you'd want to keep track of is the size of the batches. We're doing that with batch size average, well named, good. You'll want this to be as close to batch size as possible. If batch size average is consistently lower than batch size, then linker MS might not be high enough, right? You're cutting off your ability to wait for a larger batch. At the same time, if linker MS is high and your batches are still small, then it could be that records just aren't being produced quickly enough, right? And you're just adding unnecessary latency for no reason at all. Next, we have records per request average, the number of records per batch, per request. If you want to batch, this is a good sanity check just to make sure you're actually doing it. Then we have record size average. Again, this is going to help you monitor for tuning. If this value is close to or higher than batch size, then your producers aren't even batching, right? Next, we have buffer available bytes. Again, buffer.memory, this is an important thing to keep track of, and this is going to help you understand how your batching is actually occurring, how many batches you're filling up, and how quickly that memory, that buffer memory is filling, okay? Finally, record queue time average. I haven't said anything about a queue just yet, so effectively, within that batch-sized chunk of memory, we have just a queue of records that are accumulating for each batch. And so as we're building up this batch, this is a good way to keep track of how long the records are hanging out in that batch as you're trying to build it, okay? So between calling producer.send and adding that record to that batch, and when the producer actually sends a request off to the broker, that is record queue time average. Cool. So we batched. Next, can we actually send it to the broker? Maybe, but you might want to compress that data. So this is an optional step. This is one of those stages that does take additional memory on top of, for what the producer needs to be available. By default, compression is disabled. It's controlled by the compression.type configuration parameter. There are some, a handful of available compression types available. If you're not doing it and you want to get started with it, I recommend just using Z-standard as a starting point. But I encourage you to check out the docs more if you actually want to use this. Okay? So we've compressed the data, and finally we can ship off a request to the broker, okay? So this could have been a little bit of time, right? We called producer.send, and we're going to wait for some other records because we have batching enabled, and then finally, once those batches have filled, we can ship off a request to our broker, okay? And we might have multiple batches contained within this single request. If they're all destined for the same broker, great, ship them all off together. Let's be efficient. Now, every producer maintains some socket connections with some number of Kafka brokers, right, depending on which topics we're sending data to. And they're going to send these requests using binary protocol over TCP. Okay? So it's request response, right? Producers send a request to the brokers asking to store this data, and the brokers are going to send a response back saying, yes or no, did this actually work? Did we store the data? So depending on how you configure things, the producers can wait around for a response, so it's sort of synchronous to ensure that your data is actually stored, or they can just ship it and move on, okay? So it's this request process that actually kicks off this first true phase of this journey where we leave the producer and can actually get onto the broker. But before we get ahead of ourselves, there are some configurations that are directly relevant to this portion that you should keep in mind as well. The first is max request size. The default is 1 megabyte. This is, again, going to directly limit how many batches you can actually send within a given request, okay? And keep in mind that the brokers also have a limit on the maximum size of a request after compression that they can receive, okay? Next, we have ACKs, acknowledgements. This is really important. This is going to control a lot of the process moving forward. So for high availability and for fault tolerance in Kafka, you can optionally configure the topic partitions to have replicas. Okay, copies that are stored elsewhere on the cluster. So data is initially produced to a leader for that partition, the main copy that we're interacting with, and then copied over synchronously to the additional replicas. Okay, so ACKs answers the question, how many replicas should we safely write this data to before we send a successful response back to the broker? Okay, the default is all of them, ACKs all. We like that. We want our data to be stored. But you can throw caution to the wind. It really doesn't matter. You can set it to 0 or 1 if you really just want to move on with your life. Be wise about that. Okay? Think about that. Once the requests are actually sent, max in-flight connection requests per connection comes into play. So producers will maintain a connection to as many brokers as needed, depending on which topic partition we're sending that data to. But we don't want to inundate the request queue on the broker side, right? And if you also want your data to be ordered per topic partition, like maintain that ordering, you want to limit how many requests you're sending to each broker, potentially. Another important duo of configurations at this point is enable idempotence and transactional ID. So when idempotence is enabled, that's going to enforce that acts is all. Our retries, if we want to retry the sending data, is set to greater than 1, and our max in-flight requests per connection is 1. So for an individual producer session, we are ensuring idempotence of that data. Okay, if we go down for any reason, we're going to know that we can retry, or if we don't receive a response back. So you're ensuring that your data is sent. But across producer sessions, you need to be using transactional ID. If you want to make sure that when your producer goes down and comes back up, that your data is still idempotent, and then you'd make sure that it's actually sent and received, even in the event of that producer failure, then you're going to use a transactional ID to identify that particular producer. Okay, and that's going to be made producer sessions. And finally, we have request timeout MS. Once a request is actually sent to the broker, we send that request. This is the maximum amount of time that the producer is going to sit around and wait to receive a response. Okay. If it doesn't receive that response, it's going to optionally retry, right? Because the data might not have been stored. Or it could throw an exception if you don't have retries enabled. Okay? Retries themselves are handled by a couple of other configuration parameters. Retry back off in the retries. So look into those if you want to enable retries. Okay, and we're going to look at a lot of metrics related to the request as it's handled on the broker side, but I want to highlight a few that are directly applicable to the configs that we just looked at. So first we have request rate. This generally just describes the number of requests being made per second by that particular producer. Then we have requests in flight. This is a per producer metric that defines the number of requests that we currently have waiting to be filled by the brokers. You can use this to see how bogged down your brokers are, right? Or whether your producer is making an appropriate amount of requests, right? Ideally, you'd want this value to be low to ensure that your brokers are caught up and your producer isn't inundating them. Finally, we have request latency average. So once these requests are actually issued to the broker, a timer starts, right? And it doesn't stop until the producer receives a response. This metric is going to define the time it takes to make that happen. Okay? Now, let's get to the broker. But before, I want to show you what a request actually looks like. Because there's a lot of nested structures here, and I want to make sure that we understand what actually can go into a producer request. So we have the whole request. It's bound by that max request size, right? There's some metadata that's sent along with every request. So we have the transactional ID, if that's something that we've enabled. We have whatever AX is for that producer, the timeout that we're using here as well, and then we have the data that we're shipping off. And remember, this is going to a single broker, okay? And that producer data could be for many different topics. All right, so not only do we have the data destined for the Hobbit updates topic, we also have the dwarf updates, right? And we're shipping some data with one batch off to partition 1. Within the topic data that's going to Hobbit updates, we could have many partitions that exist on that single broker. And so we could have several batches with it destined for partition 0, and maybe just one destined for partition 4. All right? So that's what that looks like. Keep it in the back of your mind. It's good to just understand. And now let's get to the broker, right? We've successfully sent our request containing some number of batches off to our broker. And so our Hobbit, Bilbo, has left Hobbiton. We can finally embark on this journey. It took a lot of effort, right? That's like half of the effort just to leave the producer. So now what? Well, we're off to the broker, okay? The first stage on the broker side of things is just to look at the incoming requests, and they're going to be sent to the server socket receive buffer, okay? It's sort of a landing zone for all the data coming into the broker, and here we're going to just wait around until we're picked up by the network threads for the actual processing. There are some low-level configurations here. Usually you won't have to touch them. Or if you are just dealing with your producer clients and someone else is managing your Kafka, they're going to deal with this, and you're very unlikely to actually encounter a problem here. If you want to tweak the performance at this point, here they are for you, but generally you won't have to stray away from the defaults. From there, The network threads, whichever one is available, is going to pick up that data, pick up that request. An important thing to note here is that whichever network thread picks up this request, it's going to follow it throughout its journey on this single broker and manage it for that life cycle. Its first job is to read the request from the socket receive buffer and form it into a produce request object. Because this broker is going to be managing a lot of different incoming requests, not just produce requests. And so it's going to distinguish it as a producer request and add it to the request queue for processing. Again, there are some advanced configurations you could use at this point. Generally, you won't have to change them unless something's really wrong, but they're good to know. Right? It's good to be aware. So first, we have the num network threads. This defines how many network threads are going to be working at this point. The default is 3. Upper bound should be just the number of cores that you have available on that server. And a good way to monitor these threads at this point is using network processor average idle %. The values range from 0, meaning that the threads are fully utilized, and 1, meaning that the threads just aren't busy at all. They're fully idle. So we're on the request queue now. The network threads have picked it up. They formed the request. They set it on the request queue. And now we're going to wait to be picked up by an I/O thread to actually handle the request. So while the data is sitting here on the request queue, you have control of this area. We have the max size of the request queue with queued max requests, and we also have queued max request bytes. So you can control the number of requests and also the total size of this request queue as well. A general rule of thumb is to set queued max requests. If you're going to change it, set it to the number of active clients that you have accessing this broker. Do you know that? Not too many people know that, so maybe just leave it what it is, okay? That's a number that will fluctuate, right? So maybe it's good to not change it too much. This, by maintaining it as the number of active clients, this is going to ensure that we have strict ordering of our messages, okay? You don't want it to be greater than that because you don't want to have one request, an earlier request be dropped, and then we have another one with later records stored instead, okay? You can monitor the size of this request queue, as well as the amount of time that requests hang around in this queue. These metrics together are a pretty good proxy for giving you an idea of how well your I/O threads are actually doing and how long they're taking to process the requests once they get a hold of them, okay? So use this to figure out if your broker's overwhelmed. If the request queue is full for any reason, it's going to block, okay? We're not going to add any more requests, so this is kind of an important thing to monitor. So next up, the I/O threads, the MVPs, right? They are actually going to do the job of storing this data on disk, okay? These threads, the I/O threads, are also known as the request handler threads, which makes sense. But these words, I/O thread and handler threads, are used sort of interchangeably. Request handler threads is going to be used in the actual metrics, so we're going to switch to that. When the thread actually accesses the request, the first thing it's going to do is validate. Okay, because we've been shipping around these raw bytes for a bit, so it's going to use a cyclic redundancy check just to ensure that the integrity of this data has been maintained while it's been hanging around. Since the I/O threads actually have a lot of work to do at this point in handling this data and writing it to disk, you probably want to configure how many of these there are. The default is 8, but you can change this using num I/O threads, and the upper bound is going to be how many cores you have on that server. If you want to monitor how well these threads are actually doing, we can use request handler average idle %. Again, you ideally want this to be closer to 1, showing that your threads are idle more often than not, right? They're being efficient in how they're moving this data around. A value closer to 0 means that they're inundated. Okay, working hard. All right, so what are they doing? They're actually going to put the data where it needs to go, okay? The moment you've been waiting for, okay? We've gone through a lot of stages between calling producer.send and actually letting this data be stored on the cluster, okay? The I/O threads handling this whole portion. If you're familiar with the storage structure on Kafka, maybe, hopefully, it's a log. It's a commit log. On disk, this commit log consists of a collection of components called segments, and these segments are made up of a number of files, okay? The first is a log file, where the actual events are actually stored. And then we have an index file, okay? So in order to access the data efficiently within the log file, we keep track of an index that just points to somewhere in the log file, so we can jump around easily without scanning the entire thing and seeking. So this is an index structure that's mapping from offsets to records. Offsets aren't the only way that you can actually identify a record. You can also use a time-based index to identify them. And so we also have a time index file that just has the timestamp pointing to the record when it was written for that segment. We also have the snapshot file. So this is very useful for producer sequence numbers, which are good for idempotency. So that's also an important file that we keep track of. When the IO threads write the events to these files, all the data to these files, for efficiency, the updates happen in page cache, right? Writing to disk is expensive. So we're going to write it quickly to page cache and move on with our lives, okay? They're later going to be moved to disk. Does that worry you? Maybe. Probably it shouldn't, okay? There are a number of configurations that you can use to tweak the size of these files, how often we write to the index file, how often the files are rolled, how we clean up old data or stale data, and you can also control how often the data is flushed to disk, okay? So don't worry, you have control over that. That's not outside of your control. So I would encourage you to check the docs for more details on this if you're really going to tweak these. Usually the defaults are fine. Additionally, some of these can be overridden at the topic level. So if you have more important data in topic A over topic B, and you want to have it flushed more often or whatnot, you could also control that. A really common one is the cleanup policy. You may recall that we set this at the beginning when we assigned that topic, when we created that topic. So these take values delete and compact. Delete means that we're rolling the log file and we're going to take the oldest one and basically clean it up, right? It's not important. Compact deals a little differently, so it's going to be on a key-by-key basis. It's guaranteed to store at least one value per key, and it's going to, at a predefined interval, it's kind of like magic. It is a little bit of a black box when this cleaner actually happens, but it will go through and compact old data and remove it from the middle of the log. Okay. The best way to monitor at this stage, and the biggest one you might want to monitor, is how often the log is actually flushing to disk. Okay? And you can do this using log flush rate and time ms. It's also important to note that this entire process that the IO threads go through at this point, they're on the local broker, right? And so we describe this whole time as local time ms, the amount of time it takes for the IO threads to actually do their jobs on the local broker with that lead partition. Okay? And then, the IO threads are done, right? This is a lot of work for them. Okay, they have a lot of files to write to and a lot of things to handle, and they want to move on with their lives. Okay, so what they're going to do is just let go of the request. Okay, they're done at this point. We've made it to disk, kind of. We've at least made it to page cache. The data will make it to disk at some point, and you can configure it to be more or less a synchronous write to disk if you want to ensure that the data is written to that broker right then. Before we move on from the IO threads, I do want to touch on, there's an additional component that they will handle at this point, and that's tiered storage, okay? Tiered storage hasn't been fully released yet in open source Kafka, but some managed services of Kafka have this enabled, and this is where that happens. Since this varies depending on which implementation you're using, I'm not going to go into the explicit details, but this is where that happens, right? If we're offloading some of the data to less expensive storage, that's where this is going to happen. So once this data has been written to page cache, optionally over to tiered storage, the IO threads are done. They're going to move on. They have more expensive things to do, writing the next set of data from the other request. And so we don't want to tie them up. And they're just going to drop off the request. There's more that needs to happen here, right? Our data's only been written to one broker. It now needs to be replicated over to other ones, optionally. And so we're going to drop off the data in purgatory. This is actually what it's called. So friendly, right? We're just going to let the requests hang out in purgatory until the data is replicated to where it needs to be, okay? Remember, the data is not synchronously written to page cache. And so it's really important that Kafka uses this replication mechanism to ensure that this data is stored elsewhere as well, right? If we have it stored on all of the brokers where these copies should be, then it's probably good. We have the data we need. And it's stored, okay? So purgatory is where these requests hang out while we wait for this replication process to happen. It is a map-like data structure based on a really cool notion of a hierarchical timing wheel. Has anybody heard of those? Cool, good, because it's a really academic data structure. There are papers on this ask me to get into the details of this, I will send you the paper. But it is kind of cool. These requests sort of just float around in this cyclical sort of data structure until they're actually picked off, replicated, and we know that they're ready to go, right? Once they've satisfied the ACKS all, then we can move on from purgatory, okay? By default, remember, ACKS is set to all, so Kafka is not going to send a response back to the producer until this data is fully replicated to where it needs to go. We have our replication factor set to 3. Don't worry. This happens a lot faster than we think, okay? And this data isn't pushed from this lead broker to the follower brokers. It's waiting here until the follower brokers request to have that data, okay? And the interval that this happens over is every 500 milliseconds by default. The follower replicas know where the lead replica is for their data, and they're going to request it every 500 milliseconds, okay? So this isn't actually, the data isn't going to hang around here for that long. It's going to move pretty fast, okay? And they're going to request for this data, update their copy, and then the request can actually leave purgatory. For monitoring, the biggest metric that you want to monitor here is remote time MS. So we have local time MS, how long the request takes to be handled on the local broker, and remote time MS is the amount of time that this request sits around in purgatory, right? How long it takes for the remote brokers to actually fetch this data, okay? This metric, the remote time MS, this is factored into the entire interval of time that it takes for this request to be handled. That might seem like a silly thing to call out here, but it'll make sense in a second. Okay. Once the data has been replicated, now we can start to form a response, right? If it's been successfully replicated, we're going to say that it has, right? ACKS all has been satisfied, so we can start building up a response object that we can send back to the broker, or back to the producer, okay? We're taking this request out of purgatory and starting this response object. We can't configure the response queue like you can the incoming request queue, but you can monitor it with a similar metric. Interestingly, the amount of time that the response sits on the response queue, which is response queue time MS, this time interval is not factored into the entire time interval that it takes for the request to be processed once it hits the broker. Okay, so this time is actually subtracted out. Keep that in mind. It's kind of a wonky thing. I'll bring this up again. From there, back to the network threads, we're going to do a handoff. The network thread that picked up this request initially has still been monitoring it and handling it during this life cycle, but now it's going to sort of end its job, right? It's going to pick up this generated response and start the process of sending it back to the producer client. And finally, this outgoing response is placed on the socket send buffer to await being received by the producer. In fact, the broker is going to wait until this is actually completely received by the producer before moving on. There are, again, some low-level configurations that you can use to affect at this point. Controlling the size of this buffer, generally you won't have to affect it. And we have the response send time MS that actually describes the amount of time it takes for this response to be picked up by the producer. And this one is factored in to the overall time. So at this point, the producer has received some sort of response, right? Hopefully a good one, right? We've replicated the data, ACKS all has been satisfied, the data is stored, right? It is where it should be. And again, I want to summarize these sort of time intervals for this total process. So we have total time MS, the amount of time this whole request response takes that we're waiting for this to be fulfilled. And then it's built up with these components, right? The amount of time that the request sits on the request queue. We have the amount of time it actually takes to be processed and saved to the local broker, the amount of time it takes to replicate the data back to the other followers, and then we have the response send time MS, how long it takes for the producer to pick that response back up. And response queue time MS, not factored into that, so if you're monitoring total time MS and these metrics don't quite add up, that's why. Keep it in mind. Okay. That was kind of a journey. That was a lot. And this happens every time you try to get your data onto Kafka, right? For every piece of data, if you're not batching, that's a request, right? And so that can be a lot, right? You shouldn't take it for granted. Let's be a little responsible in how we are batching our data and be a little more efficient just to take care of our poor brokers, right? So I took you on a whole journey of just the producer client for now. It should not surprise you to know that there are other types of requests that are sent by different clients. Namely, we have the consumer client is doing pretty much the same thing. It's making a fetch request, asking for data. It might be asking for a particular size of data, right? It wants to wait for a certain amount. And so while we're waiting for that much data to be available, that request is going to be hanging out in purgatory as well until the IO threads can fetch that information and give it back to the consumer client. There are a lot of different requests that are shipped around between these clients and the brokers all the time. So next time you get a little frustrated with your Kafka, just know that there's a lot going on under the hood. Please don't take it for granted. It is that beautiful magic box that you don't really have to think about. But the next time you're frustrated, just take a step back and understand that there's more to it than it seems, all right? If you want to embark on your own journey, get deeper into this, you're curious about other metrics and configurations, I encourage you to take a look at, we have some other resources available. This is going to point to the Confluent developer portal. We have many courses, a few on Kafka internals, so if you want to go deeper into it, I would encourage you to do so. It's always good to know more about Kafka. And I'm available for questions now, and I thank you for coming. Appreciate it.